अब एक पावर पॉइंट आ गया, कोई प्रेजेंटेशन बना सकते हैं, ये तो करनी है। All the formats are there.
That's a template. Wait.
Hey, we are not creating, we are just opening Windows.
Hello, hello.
我知道，
Okay.
我没
Today
有。
we'll be covering number theory. This is going to be our second lecture on number theory. So we'll start with some warm-up problems, which hopefully you guys will know how to do because they should have all been taught in the previous number theory tutorial. So this is our contents today. Oh, and by the way, if you guys have questions, you can email us. I'll type my email in the chat, and I would invite Jay to type his email. I tend to respond slower, so I think you guys should ask Jay for help if you guys need assistance. Okay, so this is our content for today, and here's the first problem. So I'll give you guys some time to try it. Can everyone see the problem? Okay, we'll give 2 more minutes to try the problem. Okay, 5 minutes enough time to try the problem. And now I'll present the solution. Just a warning, I'm actually not sure if I'll be able to solve it. So if I take a while, you guys have to please be patient with me. Okay, so the problem was like what is the sum of all integers n such that n squared plus 2n2 divides n cubed plus 4n squared plus 4n minus 14. Okay, so how do we approach this problem? The first thing you should think of is this is n cubed and this is n squared. And we know that n squared plus 2n plus 2 divides n cubed plus 2n squared plus 2n. This is the symbol for divides, if anyone forgot. And this is true because this is equal to n times that, right? And any number divides n times itself. And then we also know that n squared plus 2n plus 2 divides n cubed plus 4n squared plus 4n minus 14. And then because n divides this thing divides this and this, it also divides their difference, right? If a divides b and a divides c, then a divides b minus c. This, if anyone needs a recap, that's because b is equal to something times a, and c is equal to another thing times a. So therefore b minus c is equal to something times a. So it's divisible by 8. So that means n squared plus 2n plus 2 divides the difference of those two, which is that, which equals 2n squared plus 2n minus 14. Yeah. And then also we do the same thing, right? And here we use that a divides a times b because ab is the multiple of 8, so it's divisible by 8. So then using the same thing, we know that n squared plus 2n plus 2 divides 2 times itself, which is equal to 2n squared plus 4n plus 4. So therefore n squared plus 2n plus 2 divides the difference of these two, which is 2n squared plus 4n plus 4 minus 2n squared plus 2n minus 14, which is equal to 2n plus 18. Yep. This is, again, we use the fact that a divides b and a divides c implies a divides b minus c. And now we notice something, right? Normally, if a number b is divisible by a, b should be bigger than a. However, n squared plus 2n plus 2 will most of the time be bigger than 2n plus 18. This is another property, right? If a divides b, then b is bigger than or equal to a, or b is equal to 0. This is the only edge case, because a divides b implies b is equal to an integer times a. And if this integer, okay, we're gonna use absolute values actually. If anyone doesn't know what absolute value is, it's the positive sign of something. So like absolute value of 3.5 is 3.5, and absolute value of negative 2. So here's something. So then that means either 2n plus 18 equals 0, which implies n equals negative 9, or 2n plus 18 is bigger than or equal to n squared plus 2n plus 2, which then means 16 is bigger than or equal to n squared, which then means n is equal to 4, 3, 2, 1, 0, negative 1, negative 2, negative 4. Those are the only possibilities. And now we have a very limited amount of possibilities we have to try. Does anyone have any questions? Oh, um, okay. This is always positive, so that means, yep, for 2n, because n squared plus 2n plus 2 is equal to n plus 1 squared plus 1, which is always positive, because square is always non-negative, so then plus 1 then is positive. This thing, and we know that this divides this. So then either this is super negative or it's super positive because it has to be bigger than this. So, um, let's see. Change actually. So if this is positive, then we know that 2n plus 18 has to be bigger than n squared. Then if 2n plus 18 is bigger than 0, then 2n plus 18 has to be bigger than or equal to n squared plus 2, which then means n is equal to 4 or 3 or 2 or 1 or 0 or negative 1 or negative 2. Yep, so then we got to try those. Ours, 2n plus 18 is negative, which then means 2n plus 18 is negative of 2n plus 18 is bigger than or equal to n squared plus 2, which then means n squared 0 is bigger than or equal to n squared plus 4n plus 20, which is equal to n plus 2 squared plus 16. This doesn't work because this is always positive, so it can't be less than or equal to 0. So we just gotta try this. If anyone would like to put them in to this, then they can. I don't want to, so that's unlucky. It also take a long time, so yeah. Does anyone have any questions? Okay, I'll count down from 5. 5, 4, 3, 2, 1. Okay, I think that means there's no questions. Okay, so next problem. What is the largest positive integer n such that n cubed plus 100 is divisible by n plus 10? We'll give you guys 3 minutes to try this. Warning die, that's a good statement. We believe 3 minutes is very enough to get some thought done into the problem, and that's why we give you 3 minutes. Also, we would like to cover more problems. However, Borning die, that was a very good problem. Thank you. Thank you for noting that and stating it to everyone. Okay, hopefully that's enough time. I would like to invite Jay Zhao to present the solution.
Okay, so I'm gonna share my screen. So Tim has to answer the question. Okay, hopefully you guys can see my screen. So like, just say yes in chat if you can see. Okay, so okay, yeah, it seems like it is working. So here's what the problem says. We have to find like an n where n plus 10 divides n cubed plus 100. And so if you remember what Houghton said from before, we have n plus 10 divides n cubed plus 10 to the n squared because we just multiply it by n squared. And then if we take the difference of these two, we get that n plus 10 divides 10n squared minus 100. Is that right? Okay, so we can do this again. We know that n plus 10 divides 10n squared plus 100 plus 100n, because because we can multiply this by 10n, we can multiply this by 10n. Now if we take the difference of these two, we can get n plus 10 divides 100n plus 100. Okay, so then we can do this one last time to get n plus 10 divided 100n plus 1,000, right? So if we take the difference of these two now, we get that n plus 10 divides 900, right? So that means that n plus 10 is has to be a divisor of 900. So since we want to find like the largest n, we're going to think about what the largest divisor of 900 is. So can someone just tell me like what the largest divisor of 100 is? Okay, this is quite sad. No one is saying anything. Oh, wow, thanks, Haotian. That was very insightful. So we know that the largest divisor of 900 is just 900, right? So that means the largest that n plus 10 can be is 900. So the largest n can be is 900 minus 10, which I believe this is 890. I could be wrong, so please correct me if I am wrong. But then so this is like the largest n that we can have is n is equal to 890. So that's pretty cool, I think. Yeah, does anyone have any questions? I'm not too sure what that means. Okay, so like how Tim did, I'm gonna count down from 5. And if no one has any questions, we're gonna move on. So 5, 4, 3, 2, 1. Okay, so yeah, let's move on, guys.
Okay, thank you for your very insightful solution. Next we will move on to new theory. This is called the Euclidean algorithm, and it states that the GCD of Q times A plus R and R is equal to the GCD of R and A. If anyone is unsure what GCD means, you might also know it as HCF, highest common factor. It is the GCD of A and B, of two numbers A and B, is the greatest common divisor of A and B. So you look at the numbers that divide A and B, and then you take the biggest one. Yep. So, can everyone find the GCD of 400 and 110? Okay, hopefully that's enough time. Guys, I'm really stuck on this problem. Could you guys please help me with this? Can someone tell me the solution? Okay, I'll count down from 5. 5, 4, 3, 2, 1. Oh, no one helped me. That's so sad. Okay, but I found out the GCD is 10, so that's the answer if anyone got it. Okay, but now we will present how to use the Euclidean algorithm. Okay, so this is what I said on the slide. GCD QA plus R and A is equal to GCD A and R. What that means is if we wanted to find GCD of 110, I mean 400 and 110, we know that 400 is equal to 3 times 110 plus 70, right? And now we know that that is equal, so then we know by the Euclidean algorithm that that is equal to 70 and 110. Yeah. I think on the slide it might have, yeah, on the slide it was in this order. Okay, and that's because we got Q is equal to 3, A is equal to 110, and R is equal to 70, right? Q times A plus R and A. And now this is equal to GCD of 70 and 1 times 70 plus 40, which is equal to GCD of 70 and 40. And that's equal to GCD of 1 times 40 plus 30 and 40, which is equal to GCD of 30 and 40, which is equal to GCD of 30 and 1 times 30 plus 10, which is equal to GCD 30 and 10. And that's equal to GCD 3 times 10 plus 0 and 10. So GCD is 10. Right, and each step I put it into the QA plus R form, and then I use the Euclidean algorithm. Alright, bam, 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 bam. So now we'll prove it. Hopefully this gives you guys a bit of an understanding of how it works. The GCD of QR plus A, plus R, the QA plus R and A is equal to GCD of R and A. And yeah, so to find the GCD of A and B, what we have to do is we consider all of the divisors of A and B, right? Consider divisors of A, consider divisors of B, consider the divisors, the numbers that are divisors of A and B, like the biggest. For example, GCD of 18 and 24. The factors of 18 are those, and then the factors of 24 are those. And then we select the common ones to both because we want the greatest common divisor, and that would be those. And then we take the biggest one, so that's by 6. And so we're gonna prove this by claiming that the factors of QA plus R and A, that the list of factors, the list of oh that's so sad. Oh, that's actually so sad. Oh my gosh. Okay, we're gonna prove that the common factors of QA plus R and A is equivalent to the common factors of R and A. And then if we can prove this, then we've proven that if these two lists are exactly the same, then the biggest number in the two lists must also be exactly the same. And the biggest number is the GCD. So that means the GCD is exactly the same. Does anyone have any questions? Okay, so if we have a common factor, if X is a common factor of QA plus R and A, then we know X divides A and X divides QA plus R. And then we also know that if A divides, okay, if we know if X divides a number and X divides another number, then X divides the difference, alright? So then we know X divides QA plus R minus A. Minus A, oh, yep. And that's equal to R because we subtract QAs. So therefore, if X is a common factor of QA plus R and A, then X is a common factor of R A. Similarly, we can also prove that if X is a common factor of R and A, then X is a common factor of Q A plus R and oh wait, I'm confused. Guys, please help me. I'm actually a bit stuck. Wait, never mind, I'm not stuck. Wait, but I'd still like to be helped if anyone wants to help me. Guys, please help. I'm actually really stuck now. Okay, never mind, I guess not. Okay, if X is a common factor of R and A, then X is a common factor of QR and A. That's because if X divides R and X divides A, then X divides R plus A plus A plus A plus A, which is equal to R plus QA. Yep. So that's the proof. Any questions? Why so many? Someone asked me why so many A. Okay, I'm sorry if this was a bit unclear. What I meant by this is subtracting. We're subtracting QAs, right? Because if we subtract, we can subtract a number. We can subtract A from QA plus R. So we just keep doing it Q times, then we subtract all Q of them, then we get R. Okay. Any other questions? 5, 4, 3, 2, 1. Okay. Here is a problem. You guys will get 3 minutes to try it. Maybe 4 minutes. Oh, okay, wait, I just realized the question is invisible. Yeah. Sorry. If you guys want a hint, then the hint is to use the thing I taught you, like just now. Okay, hopefully that's enough time. I would like to invite Jay Zhao to present his solution.
Okay, so I'm gonna assume you guys can see my screen. For the sake of not having to write GCD a bunch of times, I'm just gonna write like instead of writing this, I'm just gonna write this. So I hope that's okay. Okay, anyways, so the dn is equal to the greatest common divisor of an and an plus 1. And this, if we just like look at what they're equal to, an is equal to 100 plus n squared, and the other one is equal to 100 plus n plus 1 squared. Now if we expand out this one, we get 100 plus n squared, 100 plus n squared plus 2n plus 1. And now this looks like a bit tricky, but you can actually use the very cool hint that Hao-Tian told us, which is to use the Euclidean algorithm. So how can we use that here? Well, what we can do is we can just like take this bit out, right? So you can 100 plus n squared, and then 100 plus n squared minus 100 plus n squared. So those cancel. 2n plus 1. And okay, so what ideally what we would want to do is be able to like take this n squared out, but like we kind of can't do that right now because we have like a 2n. But like what's pretty cool here is that this is actually an odd number. So it doesn't matter if you multiply this one by an odd number, the greatest common divisor would still stay the same. Does that make sense, everyone? Okay, well, no one's saying anything, so I'm going to continue. Okay, I'll continue. So what we can do is we can just multiply this whole thing by 2 to get 200 plus n squared. Oh, plus 2n squared, sorry. And 2n plus 1. Then we can do 200 plus 2n squared minus 2n squared minus n, and 2n plus 1. And these cancel out. So you get 200 minus n, 2n plus 1. And we can do the same trick again, but we double this. So we get 400 minus 2n, 2n plus 1. And if we do the Euclidean algorithm on this one more time, or here, instead of taking away, we can add. So we can do 400 minus 2n plus 2n plus 1. And these cancel. 2n plus 1. And this is equal to 400 plus 1, 2n plus 1, which is equal to 401, 2n plus 1. Right, does that all make sense? I hope that all makes sense. And I hope that was all right. Okay, so now we can just leave it here because it's pretty nice. So we want to find the largest value of dn. And we know that that dn is the greatest common factor between these two terms. So like the biggest thing that dn can be is just this, right? Because you can't have a factor of a number which is like more than a number, or which is like more than the number itself, or if it's positive. So the biggest that dn can be would be 401. And so we can actually get that when n is 200. So because then we get 401 and then 200 times 2 plus 1, which is 401, 401, which is 401. So the largest that dn can be is 401. So does anyone have any questions? Okay, so it doesn't seem like anyone has any questions. So I think you all understood that. So that's pretty good. Oh, besides Bonning Die, Hao Tian, would you like to answer this question from Bonning Die?
Bonning Die, could you please clarify what you mean by that problem? I'm a bit unsure actually.
Yeah, if you're a bit confused, you can read over here where it tells you what dn is. So it's the greatest common divisor of these.
Oh yeah. Bonning Die. Yeah, if you read the problem. Yeah. You're welcome, Bonning Die.
Okay, so I don't think anyone else has any problems, so we'll move on.
Thank you very much. That was a very insightful solution again. Here's the next topic. This will be about the GCD, which is the greatest common divisor, and the LCM, which is the lowest common multiple of two numbers. I've already explained what the GCD is, and the LCM is the smallest number that is a multiple of A and B. So yeah, so like the LCM of 6 and 15. Does anyone want to find that? Guys, this time I'm actually serious. I can't do it. So like, if someone could please help me. Oh my gosh, thank you so much. Oh, the answer is not 3. I'm sorry. I know how to do it now. And I realize it isn't 3. Because that would be the GCD of 6 and 15. So I might have been a bit unclear in my pronunciation, but thank you very much for helping me. But the LCM, I asked for the LCM of 6 and 15, which is the smallest number that is a multiple of 6 and 15. Okay, yeah, thank you. It is study. Okay, thank you everyone for helping me. I'm so happy. Okay, so if we have two numbers A and B, right, and then we have the prime factorizations. Actually, okay, let me explain what that means first. Okay, so we're learning about the GCD and the LCM, right? And the GCD is greatest common divisor, and the LCM is lowest common multiple. So, for example, if we use the example I just gave, LCM 6 and 15 is 30, and GCD of 6 and 15 is 3. That's because if we consider the multiples of 6, right, 6, 12, 6, 12, 18, 24, 30, 36, 42, 48, 54, and so on, and the multiples of 15, then we want to find the lowest number that's in common, right? Because these are the multiples of 6 and these are the multiples of 15. 15 is not in here, but 30 is, so that's why the LCM is 30. And the GCD, hopefully you guys all know how to find. And now we'll move on to prime factorization. This was briefly touched on at the end of last tutorial. And yep, so okay, firstly as a warm-up, can everyone factorize these numbers? I'll give you guys 20 seconds. Hopefully that's enough time. So the prime factor, does everyone know what a prime is? I'll count down from 5, 5, 4, 3, 2. Okay, yeah, good on you guys. That's actually quite impressive. So to prime factorize a number, we factor it into primes. So 15 would be 3 times 5. 48 would be 2 times 2 times 2 times 2 times 3, which is also 2 to the 4 times 3. And 12 would be 2 times 2 times 3, which is also 2 squared times 3. So yeah, that's prime factorization. What's the prime factorization of 11? 11. Okay, so now I will teach you guys a new super duper cool way to find the GCD and LCM. Let's say we want to find the GCD of 48 and 42. What is it? What is it? Okay, but anyways, now I'll teach you how to find it for bigger numbers. We already know 48 is 2 to the 4 times 3, and 42 is 2 times 3 times 7. So if we format it like this, yep. And then we also know that 6 is equal to 2. times 3. And just to help you guys even more, we have this. Yeah. Hopefully you guys see it. Okay. You guys can keep trying to see the pattern here. I'll do what I can to help you. Does anyone have a hypothesis on what they think? Oh, does anyone have a hypothesis on what they think the pattern is? Okay. Thank you for telling me the GCD of 48 and 42. Okay. Anyways, the pattern is for every prime number, we take the lower power. Alright, so 48 and 42, 2, we got 4 and 1, so it's 1. 1 and 1, so it's 1. 0 and 1, so it's 0. That's the GCD. And now what if we want the LCM of 48 and 42? Wait, I don't know this. Okay, anyways, this is where we use the super duper cool strategy. Um, does anyone have any guesses as to how to do it? It's very similar. Okay, hopefully you've made your guess. We are going to take the higher power now. So that would be these, right? Because we got 4 and 1, so the higher one is 4. 1 and 1, so we take 1. 0 and 1, so we take 1. And that would be 6. 1, 2, 3, 3, 6. I think. Okay, yeah, it's 3, 3, 6. And yeah, that's because we just took the higher power. And okay, how do we prove this? Would anyone like to present their proof for why this works? Thank you, Amanat. That is 336. I'm sorry if I mispronounced your name. Okay. Here's what it says on the slide. Alright, as you can see, LCM, we just take the maximum of each, which is the bigger one. And for GCD, we take the minimum of each, which is the lower one. Okay, so to prove this, right, if we want the GCD of A and B, then for every prime, right, let's say GCD is equal to P1, or is equal to P1 to the power of C1 times P2 to the power of C2 times P3 to C3 times, this is not the number 3, this is the name, right? Like in here, okay, so this is a subscript, that's the fancy name. It's like the lower number in the bottom right. So GCD A and B divides both A and B, then that means the power of P1, which is C1, must be less than the power of P1 of A and B. So C1 is less than or equal to A1, and C1 is less than or equal to B1. You guys can think about it for a bit, right? Because if the power is higher, then it won't divide. Yeah. Um, A number divides another number if and only if the power of every prime is lower. It's quite easy to prove, but maybe it's a bit difficult to understand at first. So maybe you guys should think about it. Okay, so if we continue, then we get this and so on. And we want the GCD to be as big as possible, right? It's the greatest common divisor. So therefore we want C1, C2 to be maximum. So therefore C1 is at most minimum of A1 and B1. And therefore C2 is at most minimum of those two. And that's how we get that. And for the LCM, let's say LCM AB is equal to P1 D1 times P2 D2 and so on. A and B both divide the LCM, so therefore that means A1 is less than or equal to D1 and B1 is less than or equal to D1. So that means D1 is at least the maximum of A1 and B1. And we keep going, and that's how we derive that one. Okay, next problem. Does anyone have any questions? Here's the problem. Okay, wait, as a hint, this problem has zero relation to what I just taught. You guys can have 2 more minutes, 1 more minute to try it. Someone asked a question. Okay, maybe you guys get 2 more minutes then. It says starting with, okay, when the activator, what's it called? When the button is pressed the kth time, the doors that are multiples of k are activated. Activated means opened or closed. So if the door was originally closed, then when it's activated or open, and if it was originally open, then when it's activated, it will be closed. So for example, door 10 on the first time will be activated, so then it opens. Then on the second time it closes. Then on the fifth time it opens. Then on the 10th time it closes. Okay, it seems like some people are struggling a bit. So the hint is to maybe play around with the first few doors, and then you might notice a pattern with some of the doors and which doors are open or closed. And especially maybe there's something to do with the square numbers. Yep. Okay, I'd like to invite Jay Zhao to present his solution.
Okay, I think you guys can see my screen. Okay, so I think if you've tried some of the small numbers, if you tried like the numbers 1 to 9, you might notice that the doors that remain open at the end are from 1 to 10 are 1, 4, and 9. And so what's interesting about these numbers are that they're actually all squares. So I'm just gonna tell you guys that like all the square doors do in fact stay open at the end, and then all the non-square doors don't stay open. So we're gonna so I'm gonna show this. Okay, so for each, if we consider a single number, since all the numbers are less than or equal to 100, that means from all the factors are between 1 and 100. So for every one of, so let's just consider like, for example, let's look at 24. It has the divisors 1, 2, 3, 4, 6, 8. What other divisors I have? Oh, 12, 24. Please correct me if this is not all the divisors. So these are the divisors of 24. And for each of its divisors, it gets activated 1 time. And all the doors that stay open at the end have to be activated an odd number of times. Because if the door gets activated an even number of times, it opens and then it closes and then it opens and then it closes, right? So at the end it closes. So all doors that stay open at the end have an that's such a bad odd number of divisors. And for a number that is not a square, we're gonna show that it has an even number of divisors. So if n is not a square, then for each of its divisors, we can pair it up with the divisor n over d. So for the case of 24, it would be like if you had 2 and 12, you can pair these up. So if we look at 24, we can pair up 1 and 24, 2 and 12, 3 and 8, 4 and 6. So it gives us an even number of divisors. And then this doesn't work for squares because if we consider the square, let's say 36, it has the divisors 1, 2, 3, 6. Damn, what other divisors does it have? 18. Wait, this is kind of hard, guys. Can you tell me what divisors it has? Four, 9. Oh yeah, 9. 12, true. 18. And yes, okay, I think that's it. I hope that's it. Okay. So what we can see is that let's just use the same pairing idea from before. If we pair 1 and 36, that's 1 and 36 over 1, and 2 and 18, and 3 and 12, and 4 and 9. So all of these, that's like an even number, right? But then one of its divisors is like 6 is equal to 36 over 6. So you can't pair it up with anything. For even numbers, for not even numbers, for squares, there's like an odd prime out that can't be paired up with another divisor. So that means it has an even number of divisors. And we've said before that all doors that stay open at the end have, I meant to say odd, but all doors that stay open at the end have an odd number of divisors. And squares are the only numbers that have an odd number of divisors. And so the only doors that stay open at the end are squares. Okay. I'm hoping that made sense to everyone. If you have any questions, you can ask them now. Okay, I'll count down from 5. 5, 4, 3, 2, 1. Okay, let's move on.
Thank you for your very insightful solution again. So now we'll move on to the next problem. Yep. Something very tricky here is we're actually taking the lowest common multiple of 3 numbers. You guys can try to figure out how that works. We'll give you guys 1 minute to try this problem. Okay, hopefully that's enough time. Okay, I've actually prepared a little table to make it fairer to see. So, I'll paste the problem. Here's the problem. Hopefully that's big enough to see. So the least common multiple of 6 to the 6, 8 to the 8, and k, and it said that it's equal to 12 to the 12. So, firstly, let's prime factorize these numbers, which I've done. And then let's say k is equal to 2 to the p1, 3 to the p2, 5 to the p3, 7 to the p4, and so on. Right, these are just all the primes. And obviously, like, p could 0. And so what is the least common multiple of 6 to the 6, 8 to the 8, and k? It would take, for each prime, it would take the highest power of all 3 numbers. Because the power has to be bigger than all 3, because it's divisible by all 3 as a multiple of all 3 numbers, and we also want it to be the least common multiple. So it's bigger than all 3, and we want it to be as low as possible, so we take the highest of those 3 numbers. So that means 12 to the 12 should be 2 to the power of the biggest of those numbers times 3 to the power of the biggest of those numbers. And for the remaining primes, it will just be 5 to the p3 times 7 to the p4 times 11 to the p5 and so on. And as you can see, in the prime factorization of 12 to the 12, there are no 5, 7, 11s, and so on. So immediately these are 0. Right. And then we know that the maximum of 6, 24, and P1 should be 24. So that means P1 has to be less than or equal to 24. And then we also know the maximum of 6, 0, and P2 is equal to 12. So if we think about it, what does that make P2? One of these numbers has to be 12, right? If 12 is the maximum of these three numbers, then one of them has to be 12, and these two aren't. So that means P2 is equal to 12. And P1 is less than 24. And P1 also has to be bigger than or equal to 0, because we can't have a negative power of a prime. It just doesn't work. And that's 25 possible numbers. So the answer is 25. Does anyone have any questions? Okay, moving on. We actually have a super duper cool problem. This is a IMO problem. One of the hardest IMO problems ever asked, actually. So you should be very proud of yourself if you solve it. However, don't be actually you should view the problem as very easy. So therefore you have more confidence. Yeah, but it's not that hard. Actually, I will not comment on its difficulty. Yep. You guys will have 2 minutes, 1 minute to try this problem. Oh, okay, wait. Some people are confused about the term irreducible. So, for example, 12 over 8 is reducible because 12 over 8 is equal to 3 over 2. Yep, that's your hint. And for example, 3 over 2 is not reducible because you can't simplify the fraction further. Okay, hopefully that's enough time to try the problem. So the problem was, let me find it. Prove that for all natural numbers n, the fraction 21n plus 4 over 14n plus 3 is reducible. By the way, natural numbers are the positive integers. So 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I said that 12 over 8 is reducible because 12 over 8 is equal to 3 over 2, and 3 over 2 is not reducible. irreducible. What's our hypothesis on what constitutes a reducible or irreducible fraction? For example, 16/8 is also reducible. Okay, so a fraction is reducible if okay, that's correct. Josie is correct. That's very smart. Is reducible if A and B have a common divisor. And A over B is irreducible if A and B have not. So we want 21n plus 4 and 14n plus 3 to be irreducible. So, yep, that's correct. Thank you for your help, everyone. This is a really tricky problem, so it's amazing that you got that far, and I can't get that far, so I'm very grateful for your help. So we want GCD n plus 4 and 14n plus 3 to be 1. This is where it's a bit tricky. So let's GCDs should remind us of the Euclidean algorithm. QA plus R and R is equal to, QA plus R and A is equal to GCD of R and A. If we try using that, thank you for that. Oh yeah, thank you. That's correct, thank you. Okay, if we try using that thing on here, then we get GCD of 21n plus 4 and 14n plus 3 is equal to 7n plus 1 and 4 plus 3. And right, because we subtract 14n plus 3 from this, and then we get that. 7n plus 1 we got from 21n plus 4 minus 14n plus 3. Okay, and now with that, would anyone like to try finish the problem? Okay. Manat said 3 times equation 1 minus 2 times equation 2 is equal to 1. I'll assume you meant 3 times this one minus 2 times this one. So 3 times 14n plus 3 minus 2 times 21 plus 4. Which is equal to 42n plus 9 minus 42n minus 8 is equal to 1. That is a way to solve it actually. Because GCD 2n, if we multiply, right, if we go GCD of A and B, that's going to be at most GCD of A times some number and B, because now we're just increasing all of the numbers. So that would be at most GCD of 2 times 21n plus 4 and 3 times 14n plus 3. Thank you. So now we get this, right? Which is equal to GCD of 42n plus 8 and 42n plus 9. So if we subtract using, and that's equal to GCD of 42n plus 8 and 42n plus 8, 1. And we can even add 1 times that. So now using the thing we learned, we can now subtract this from that. So we got GCD of 42n plus 8 and 1, which is 1. And now you're done because you've proven the GCD is 1. Well, it's actually less than we.
吃莲肉全部都还很香的，其实。
Okay, so the GCD is less than or equal to 1. And it has to be at least 1 because it's the GCD. It's a positive integer. Therefore, it's equal to 1. We're done. But we can also do it this way, right? That's equal to GCD of 7n plus 1 and 2 times 7n plus 1 plus 1. which is equal to GCD of 7n plus 1n more, which is equal to 1. Either way works. If anyone has any questions, please ask. Okay, so now we'll move on. Modular arithmetic. We briefly covered this last time. I'll give you guys 30 seconds to try those examples. Okay, hopefully that's enough time to try the problem. Okay, as a recap, A, this is read as A is congruent to B mod C. And that's meant to be a triple line equal, but I can't type it. So, yep. This means A leaves a remainder of divided by C. So, for example, 13 is congruent to 1 mod 4. 17 is congruent to 3 mod 7. I'm going to try these examples. What is 54 congruent to? Mod 13 is congruent to 2 mod 13. 29 is congruent to 2, 9. What is congruent to 17 mod 31? There's a lot of solutions, and one of them would be 48. And 36 is congruent to 46 mod what? There's two solutions here, right? It could be 1 or 17. Okay, thank you for your help, everyone. Yep, you got them right. That's very impressive. So now we'll move on to a cool theorem. Actually, let's change the order. Let's teach this one first. So here are two very similar theorems, Euler's totient theorem and Fermat's little theorem. Okay, someone asked how could it be 1? The question was 36 is congruent to 46 mod what? And oh, okay. I've been teaching a simplified version of mods. So yeah, let's ignore this one for now. That's not important. I'm sorry for putting that in. 17 would be the better answer. If anyone wants to be more advanced, A is congruent to B mod C is equivalent to C divides A minus B. And then that means mod 1 works because 1 does indeed divide 63 minus 46. But then in here we get so many solutions, right? We get 4, 1, 5, 9, 17, 21, 25, 29, 33, so on. We also got -3, -7, -11, -15, and so on. So many solutions if we do it that way. So yeah, this would be the proper definition. I've just been doing the remainder because that's mostly all you need to know. Good question. Okay, here's Euler's Totient theorem and Fermat's Little theorem. So, yeah, you can just have a minute to read what it says. Oh, wait, is it Totient? Euler's something theorem. Euler's theorem, yep. Okay, hopefully you guys have had enough time to read it. So if the greatest common divisor of a and m is equal to 1, okay, firstly we gotta clarify what that function in the exponent means. It is the number of positive integers that have GCD 1 with that number. So for it's called phi. So phi of 11, I think it's called phi. Yeah, we'll call it phi. Phi of 11 is 10 because 1, 2, 3, 4, 5, 6 up to 10 are all less than 11 and all have GCD of 1 with 11. Phi of 8 is 4 because 1, 3, 5, and 7 have GCD 1 with 8. Phi of 9 is 6 because 1, 2, 5, 1, 2, 4, 5, 7, 8. So, yeah. And that's all we need for now. We can ignore Fermat's Little theorem for the moment. So, this one, you can try proof. It's quite a cool proof. There's a lot of proofs for it, but it's not very simple. So I will not be presenting it today. Okay, but what it said was if GCD A and M equals 1, then A to the phi of M is congruent to 1 mod M, I think. Yeah. So for example, if we have 5 and 7, then GCD of 5 and 7 is 1. So that means 5 and phi of 7 is equal to 6, right? Because we have to consider 1, 2, 3, 4, 5, 6. And they all have a greatest common divisor with 7 of 1. So therefore 5 to the 6th is congruent to 1 mod 7. Right? Because that's A, phi M, and M. And indeed, 5 to the 6th is equal to 15625, I think. Hopefully that's correct. And 15625 divided by 7 is equal to 2, 2, 3, 2, remainder 1. So, yeah, we can check that it is 1. Another example, and here I use 2 primes, right? They don't have to be primes. We can have like A is equal to 6 and M is equal to 11. Okay, let's do 5. Okay, but it doesn't have to be 5. But yeah, in this case, 6, A is not a prime. GCD is still 1. Phi of M is equal to phi of 5, which is 4. Actually, let's swap them. What's phi of 6? Everyone think about it for a bit. If we consider the numbers less than 6, then the GCD of 1 and 6 is 1, so it's good. But 2 and 6 is 2, which is not 1. 3 and 6 is 3, which is not 1. 4 and 6 is 2, which is not 1. And 5 and 6 what? So phi of 6 is 2. So therefore, we got this, which is correct, because 5 squared is 25. And 25 over 6 equal to 4 are 1. And just as an example, what happens if the GCD is not 1? Let's say A is equal to 4 and M is equal to 6. 5, 6 is equal to 2, then we got 4 squared is congruent to 1 mod 6. Which means 16, 4 squared is equal to 16, and 16 is equal to 6 is equal to 2 power 4. This is not the same. 5? Sorry, what do you mean by 5? Oh, phi? You mean phi? Okay, I'm waiting. Okay, that's fine. It's okay. And yeah, if we look back now at the other theorem, Fermat's little theorem, states for all primes p and integers a, such that p does not divide a to the p minus 1 is congruent to 1 mod p. This one we can actually prove. You guys can have a minute to try proving it. This lesson will go a bit over time. It will go 8 minutes roughly over time. So if you want to stay, you can stay. If you have to leave, or if you want to leave, then you can leave if you want to. But it will finish in around 8 minutes. Okay, hopefully that's enough time to try prove it. So we want to prove that if p is our prime and p does not divide a, then a to the p minus 1 is congruent to 1 mod p. And yeah, we know by Euler's quotient theorem, if GCD A and M is equal to 1, then A to the phi M is congruent to 1 mod M. So the hint is to use this theorem to prove this theorem, which is Fermat's little theorem. How do we do this? P does not divide A, and P is a prime. So what does that mean the GCD of P and A is? It's 1. Because the GCD has to divide P, and the only two divisors of P are 1 and itself. And P doesn't divide A, so therefore it has to be 1. So by Euler's quotient, oh, and then we also know that phi of P is equal to what? What is it equal to? If we consider the numbers less than P, how many numbers have a common divisor with P of 1? 2 is a reasonable guess, but it is not correct, unfortunately. Look at all these numbers. For example, if we consider 7, and we got these numbers, how many numbers have a GCD of 1 with 7? Yep, it's 6. That's correct. Because all of these have a GCD of 1 with 7. Because 7's a prime, right? So the GCD of 7 with any of these numbers is 1. And more generally, phi of P is always equal to P minus 1. So therefore, by Euler's quotient theorem, a to the phi of p, because now we're letting m be p, congruent to 1 mod p. But we also know that's just p minus 1, so now we know a to the p minus 1 is congruent to 1 mod p. And we're done. So that's the proof. So for example, we have a prime 7, p equals 7, and let's say a is equal to 5. 7 does not divide 8. So 5 to the 7 minus 1 is congruent to 1 mod 7. And what was it? 5 to the 6 is equal to 15625. Oh wait, this was the example I did. Oh, okay. Yeah, but yeah, that's true. 5 to the 6 is congruent to 1 mod 7. And finally, we have one more theorem, which is Chinese remainders theorem. I'll go over this very briefly so we can finish quickly, and then you guys can go to bed or whatever you want to do. If we have a number x, and we know, and we want to, no, we don't have x, we want to find x, and we know x is congruent to a1 mod b1, and x is congruent to a2 mod b2, and we have n of these, so x is up to x is x has a remainder of an mod bn, and all the b's are pairwise relatively prime, which means for any two b's, bi and bj, where I and j are not the same, so two different b's, their greatest common divisor is 1. Then there is exactly one solution for x mod b1, b2 up to bn. So let me demonstrate what this means. If we consider the example, x is congruent to 3 mod 5, and x is congruent to 4 mod 11. So we're claiming mod 55, there's exactly one answer for x. Just think about it. So x is congruent to 3 mod 5. So this means x is equal to 3, 8, 13, 18, 23, 28. One of these. This one is also not too easy to prove. It's not very beginner friendly. So I will not prove this one. But I will give you some intuition on how to use it. And we also know that x is congruent to 4 mod 11. So x is equal to 4, 15, 26, 37, 48. And obviously this list keeps going, right? But we just want to consider the numbers below 55. Because it's pretty clear, like, if, okay, for example, x equals 48 is the solution, right? 48 is congruent to 3 mod 5, and 48 is congruent to 4 mod 11. That also means 48 plus 55, 48 plus 50. These are all solutions. And that's why we're considering the numbers under 55, which is 5 times 11. And if we look at the description of the theorem, it says mod b1, b2 up to bn, so the product of the mods. And indeed, if we look at the numbers below 55, there's only one remainder in common, right? And that's 48. So therefore, x has to have a remainder of 48 mod 55. Let's look at one last remainder, and then that'll be it for... Oh, okay, there's one solution for x in this mod, right? Because there's infinite solutions for x, there's all of those. but they all have the same remainder when divided by b1 times b2 times up to bn. Good question. So let's say x is congruent to 3 mod 5 mod 6, x is congruent. Also, in this example, you'll notice that 5 and 11 are both primes. That doesn't have to be true. But they do have to all be coprime, right? So for example, if now do this, that doesn't work anymore. It might still work. Okay. 6 and 8, GCD of 6 and 8 is 2, which is not 1. And therefore it doesn't work. For example, so now x is congruent after the first one, that means x is congruent to 3 or 9 or 15 or 27, 33, 39, 45, mod 48. And this means that x is congruent to 6, 14, 22, 30, 38, 26, mod 48. If you compare the two lists, you actually notice nothing is in common. X, there is no solution for x. So yep, sometimes it does work though, but it always works if all of the numbers are relatively prime. Now for one last example, let's try it with 3 congruences. X is congruent to 3 mod 6, x is congruent to 1 mod 5, x is congruent to 7 mod congruent to 0 mod 7. So the theorem states that there should be one solution for x mod times 5 times 7, which is equal to 210. And okay, this is not going to be easy to find. Okay, let's first consider the first two. And let's simplify this, right? Because the theorem states given a system of congruences, we can combine them into one. So we know there's one solution from those two, mod 30. What is it? It is wait guys, I'm really stuck. Please help. Oh, this is good exercise actually. Yeah, what is from these two? What must x be? Mod 30. 21, that's correct. There's no real good way to find that it's as a remainder of 21. The important part of this theorem is not that we can find the remainder, but it's more that there exists a remainder. If you look at, there's some problems in the handout that will use this theorem, and they will all only use the fact that there is a remainder. It won't ask you to find the remainder because that's not easy to find. But yep, 21 is correct because 21 has a remainder of 3 mod 6 and 1 mod 5. But those two become this. So now those 3, excluding this one, becomes these two. And now, oh, actually pretty nice. Right? What is it congruent to? Mod 210. Does that mean the whole two? Yep. It is 21 because if we look at the original problem, x is congruent to 3 mod 6, x is congruent to 1 mod 5, x is congruent to 0 mod 7. Then we get 3, 9, 15, 21, 27, 33, 39, and so on. And we got 1, 6, 11, 16, 21, 26, 31, 36, and so on. And we got 0, 7, 21, 14, 21, 28, 35, and so on. And we already see a number in common. Also, as the theorem states, there is one distinct solution. So if we found one solution, 21, then we know the solution is 21. Okay, that's it for this theorem. Does anyone have any questions? That's it for this week's tutorial. If no one has any questions, then the tutorial is finished. Bye. You're welcome. You're welcome.